I'll begin with a prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. To pray with this day, help us to, again, Lord, glorify you, what we do, Lord. In your name I pray. Amen. All right, so let me continue with the story of Laplace transforms. It seems kind of dark in here, doesn't it? I'm going to put the shades up, actually, because it's kind of... Let's see here. Almost. There we go. Okay, so let's continue with Laplace transforms. I suppose I should probably collect your test before I forget. Test 2. So make sure your name's on there. I'll pick them up. I'll let you pass them over and I'll get them. So today we're going to look at the discontinuous functions. All right, and so before I get even to Laplace transforms, I just want to show you guys some useful tricks, if you will, because you know, what's our notation at the moment for expressing piecewise defined functions? What do? I guess we really only have like two techniques, right? We could draw a graph, or we can give a case-wise defined function, right? Like this. So f of x. Oh, I should use t here. We should use t. So, for example, I'll start with an example. We might have f of t equals to, let's say, t squared for 0 less than t less than 2, and then maybe it's sine t for t greater than 2. You can throw equality in either case, doesn't really matter. Okay, so this is a discontinuous function, right? When you get to 2, t squared is at 4. When you plug in 2 into sine, you don't get 4, right? Because sine is stuck between plus or minus 1. There's a jump discontinuity there. So there's, question, what is a nice formula for this? Let me show you how to do it. So what we'll do is we'll say t squared times u of t, all right? And then, so this basically what this does is it turns on, this turns on the t squared at time 0, and then I subtract u of t minus 2 like this. Now let me explain to you what this u I'm using is the unit step function. So here's the definition. U of t minus a, all right, is by definition, fine, let me back it up a second here. Forget about the a for a second. What's u of t defined to be? U of t is the unit step function. This thing, 0 for t less than 0, and it's 1 for t greater than or equal to 0. Actually, I don't know, honestly, folks, whether the equality goes with one or the other. It doesn't really matter. Okay? So this is so-called unit step function. So like what is u of t minus 2? How's that work? Well, that means if you think about the substitution, if u is less than 0, right, if I think about this being, u is a bad substitution variable here. How about s? All right, if I think about, still a bad choice. Lambda. Think about this being lambda. If lambda is less than 0, what does that amount to? T minus 2 less than 0, right? In other words, t is less than 2. So it's 0 if t is less than 2. All right? And it's 1 if t is greater than or equal to 2. And of course, there's nothing especially special about 2 here, is there? I mean, I could just as well put an a there and have u of t minus a. It'd be 0 all the way up to time a, and then it'd be 1 past time a. So if you look at the thing I've written in parentheses so far, what does this do? This becomes 1 when you put time equal to 0, right? And this stays on forever and ever. This is always 1 for all positive time. In these examples, we don't generally care about negative time. So we start everything at time 0. That's just the world in which we live here mathematically. All right, so this turns on time 0 and just stays on at 1. Then at time 2, what happens? At time 2, this thing starts being 1. Now before time 2, like time 0 to time 2, this was 0, so it didn't do anything. But at time 2, this becomes 1. So then you got 1 minus 1, which is 0, effectively nullifying this term. Right, so this basically turns on at time 0 and turns off at time 2. That takes care of case 1. So then I do plus sine of t. And so what we do is we turn this on at time 2 with this, right? And then, much like the lights in my children's room, we never turn them off. Like it's sine t forever and ever, game over. And so there you go. I don't need the parenthesis here really, because you just sort of leave that on. And that's a formula for that case-wise defined function in terms of the so-called unit step functions. Let me give you a definition. So these are the unit step functions. Sometimes these are credited to Heaviside. Heaviside's also, I'm trying to remember. I want to say he has something to do with the story of vectors. I have some other name bouncing in my head. I can't think of it. Now, I should make a definition here. The gate function. Now, if you look at my solutions from previous years, I don't always embrace this idea, but as longer I teach this, the more I think it's important to make this part of the discussion, just to give this thing a name. So the gate function, what it is it turns on at time t equals to a, and then turns off at t equals to b, right? And here I'm assuming a is less than b. So we could use the notation g, a comma b of t for that, right? And there's a formula that's nothing more than u of t minus a minus u of t minus b. For example, that's what I did right here, right? This is G02, right? I suppose if you want to, you could say that this is just the, I mean, I suppose it would be reasonable sort of common notation say that this is G of 2 comma infinity, but I don't usually, I mean, you can make that definition if you want. Say if we don't, if we don't subtract something from the top, then it's just, it goes on and on, right? So a unit step function is kind of a silly example. It's a gate function that doesn't ever turn off. Here's the graph. Very boring. A, B, and everywhere else. I'd actually rather, I mean, I don't know. I have thrown equality in here, but you could throw it out. I'm not really committing to what the value is at the discontinuity, okay? So, and these, of course, are not really in the graph, are they?
That's just the gate function, not the f of t function, right?
Yep, that's just the gate function. The f of t function is something weirder, right? This actually would look something like So it's t squared, right? Up here to, say, time 2. So this would be 4. My graph's not very good. Sine of 2 is, it's on its way to pi, right? So, let's see here, if I could think. Right. So that's a graph of this thing. I suppose if I'm going to be true to my inequalities, I should put the circle here, eh? But yeah, that's a formula for that. And we'll see today how to take the Laplace transform of such things without breaking into cases. That's the cool thing. Let's do one more example. I call this example 1. Example 2. Let's look at f of t equal to, I don't know. How about sine of t squared, 0 less than t less than pi, and say e to the t for pi less than t less than 10, and then let's say t cubed for t greater than 10. Again, I don't really care about what the value is at the discontinuities. All right, so here we go. F of t, well, I just do it here. So what we want is we want sine of t squared times the gate function from 0 to pi plus e to the t times the gate function from pi to 10, and then plus t cubed. And I'll just write it in terms of the unit step function of t minus 10, right? To be more explicit, this is the sine of t squared times parentheses u of t minus u of t minus pi, right? Plus e to the t times u of t minus pi minus u of t minus 10 plus t cubed u of t minus 10. Now, depending on the kind of professor you have, you might have a different professor who would just teach you this. You just write down this, like some sort of black box. There'll always be like a gathering of terms from different gates that have matching times, like the pi times go together and give me like an e to the t minus the sine of t squared. And then there's also this, for 10, I've got t cubed minus e to the t times u of t minus 10. So you can always gather together terms like that. So it'll be a sum of functions times unit step functions. So basically, if we learn how to take the Laplace transform, basically we need to learn how to take the Laplace transform of like a function times a unit step function. If we can do that, right? If we can learn how to take the Laplace transform, we just need a formula, right, for the Laplace transform of something like f of t times u of t minus a, right? If we can get that formula, then what can we do? We can take the Laplace transform of these sorts of things, right? Okay, so that's where we're headed. Now that you know a little bit about, what is a gate function. So computationally, your first sort of task is learning what I've just shown you here, how to convert functions to the unit step function notation. because we have to be able to do that in order to use the technology which will develop past this point. Okay. So let's see here. What is the Laplace transform of f of t? Well, I guess I should start with something a little bit easier to get us started. How about what's the Laplace transform of the unit step function itself, right? I mean, I think we probably could take this as a subcase of the calculation I'll do after it, but it's useful just to do this alone because it gets the main ideas in your head. So we have the integral from 0 to infinity. I usually write the exponential first. E to the minus st, u of t minus a, dt. Which is what? This is the same as the integral. So the cool thing about this unit step function is it's really kind of boring. How's it work? It's 0 until time a, right? And then it's just 1. So all this really does is change the bounds. It gets rid of time 0 to time a, right? They're gone. We're integrating 0 up till time a. So we can just change this to the integration from a to infinity of e to the minus st dt. Because again, u is 1 for time a to time infinity, and it's 0 before that. So that's, you break the integral into cases, and that's all that's left. Does that make sense? Do I need to write more? Do you guys understand? Okay. And then you integrate. So this is, minus 1 over s e to the minus st, evaluated from a to infinity. The infinity term drops out, provided that s is greater than a. So this is just going to give us 1 over a. I'm an idiot. We're evaluating, this is for t, right? The integration's in t, not in s, isn't it? So 1 over s. Fine, I'll write it out just a second here. Minus 1 over s e to the minus s times infinity. Plus 1 over s e to the what? So this, actually, I don't need s greater than a. This drops out for s greater than 0, right? So I get 1 over s e to the minus, I'll say as for s greater than 0. So there you go. There's another Laplace transform to add to our list. Okay. How does this square against, you notice that we have f of t equal to 1, right? Since we consider positive times, this is the same as u of t, right? So check out how this works. If we just look at the constant function 1, and we're always considering positive time domain, right? That's ubiquitous through everything we're doing. We're considering positive time. Time starts at 0. That's the world in which this chapter lives. So this is that. How does this deal with the Laplace transform of 1? So the Laplace transform of 1, we know before was 1 over s, right? But you know what? The Laplace transform of u of t, guess what that is? It's 1 over s times e to the 0 times s, right? Also known as 1 over s. So this is consistent. And as a general point of order, when you have a term that you're calculating the Laplace transform of, like this one, for example, sine of t squared times u of t, you can essentially just drop out the u of t and it doesn't change anything. So the unit step function based at time 0 is kind of, I usually write them just for the sake of sort of symmetry of algebra, but pragmatically speaking, it doesn't do anything to the math here. Because we work with time 0 to infinity. Because the whole Laplace transform is based off the assumption that time goes from 0 to infinity for our functions. It's right here. If you wanted to work with functions with infinite time domain, you'd have to do something like replace this with minus from minus infinity to infinity or something else. I don't know what happens there. I'm not an expert. But anyway. Okay, so let us attempt to figure this out. So what's the Laplace transform of a function? Let's assume it's a Laplace transformable function. F of t times u of t minus a. How's that go? So let's calculate this. Integral from 0 to infinity, right? And then we have e to the minus st, u of t minus a, dt. Oh, forgot something. Very important something. F of t. So same song and dance. This is the integral from a to infinity of e to the minus st, f of t, dt. How do I know that? So between 0 and a, it's killing this function. It's gone. It's nothing there. So the integration really, as far as the non-trivial aspect of it, starts at time a. So we have the integral from a to infinity of e to the minus st, f of t dt. Now, so what we want to do is we want to see this as the Laplace transform of some related function. Or, we want to convert this to a Laplace transform. The way to do that, right, is to make the integral go from 0 to infinity. So how can you change the a? How can you make a go to 0? Ew. Oh, sorry. Oh, my goodness. What I left on the board, who knows? It could be contagious. Let's see here. Literally, right? Let's see here, t. So if t is equal to a, we want u to be equal to something to be equal to 0. Maybe we should use t minus a as a substitution variable. Because if I use t minus a equals to u, that makes t equals to a become u equal to 0, right? So I should make this u equals t minus a substitution to make the bound go from 0 to infinity instead of a to infinity, right? If I do that, how is t and a related? Well, t is equal to u plus a, right? And dt is equal to du, right? So here's my u substitution. So I have e to the minus s times what? Times u plus a. F of t is now f of u plus a. And dt is du. All right, one more step here. That is really, I can bring an e to the minus sa out front. So I use the law of exponents. E to the minus su minus sa is e to the minus su times e to the minus ua. But the e to the minus sa has no dependence on the integration variable whatsoever, right? So it's a constant with respect to the integration. I can pull it out front. And then what I'm left with is the Laplace transform of something, right? It's the Laplace transform of not f, right? It's the Laplace transform of f of u plus a, right? At s. But it's weird to write it that way. And so instead of writing a u, we usually write a t there, because it's just a dummy variable of integration. So we can put a t here. And there you go. That is one of the formulas. Do you guys all have your sheet? I think I have left my sheets at the office, unfortunately. Oh, thank you. So check it out. We just derived, I believe, 8. Right? We just derived 8. It's the equation 8 that's sitting under table 7.2. But this basically is our formula. This is how we calculate the Laplace transform of a function times the unit step function. This is the equation 8. not to be confused with Theorem 8. What's Theorem 8 about? Theorem 8 tells us something related, right? It says the Laplace transform of, and I used it, if you want me to make it look like 8 more completely, if you want to. Do you want me to make it look more like 8 completely? I change the letter F to the letter G, then it's exactly the equation, right? I'll do that. I mean, if we can prove it for F, we can prove it for G, right? No big deal. So the Theorem 7 concerns the Laplace transform of F of t minus A times U of t minus A, right, of S. So here, let's just make the substitution. We'd be letting G of t, right, equal to F of t minus A. So the theorem we just proved, the equation 8 we just worked through, would give us what? It would give us e to the minus as, right, times the Laplace transform of what? Of, g of t plus a, right? But what would that be equal to? If g of t is f of t minus a, that means g of t plus a. This is f of t plus a, parentheses, minus a, right? In other words, this is just the Laplace transform of f of t. So by this simple substitution, we kind of find the inverse. Let me just write it over here. So just to emphasize what we got is that the Laplace transform of f of t minus a times u of t minus a at s is equal to e to the minus as. You'll forgive me if I erase some of our derivation. I think do you guys have any questions about the derivation? It's actually pretty straightforward, right? I mean, like, it's one of these weird things where the derivation is actually way, way easier than the implementation of the theorem. Like, a lot of times, proving the theorem is much harder than using the theorem. This is exactly the opposite of that. You'll see. And it's all about function composition, too.
I like it the other way.
Yeah, because I don't.
We only proved one.
Yeah, and we don't usually ask you to prove things, at least in these courses. Don't worry, I make up for that in like Math 321. So,
Is it not
that's the thing, is it's f of t, but the input's different. Here, we're inputting f of t minus a times u of t minus a. In contrast, here we had g of t, right? Now, this isn't really what's interesting. What's really interesting is the corollary to this, which is what we actually use, which is that the inverse Laplace transform of e to the minus as times f of s, all right, at time t is equal to f of t minus a, u of t minus a. So let me emphasize here, the heroes of this story are really what I'll put in the red box, these guys. These two are the things we are using over and over and over again as we get into the details here, combined, of course, with the gate function to make things have the appropriate format. Let me work an example now that we have the necessary toys. I'm going to erase this before I'm tempted to take the Laplace transform of it, which would be awful. Truly awful. I don't know. Actually, guys, I don't know if I have the necessary technology to take the Laplace transform of the sine of t squared. I think that's actually outside our calculational province. Unless you want to convert it to a power series in t and then do term-by-term Laplace transforming, which is a thing. There are problems in your book about that. Maybe we'll talk about that next time. Like, let's not do that, though. Okay, so, as advertised, finally. a example. So suppose we're trying to solve y prime prime plus y equal to f of t, where f of t in this case is 1 for 0 less than t less than 2, and it's t squared. Oh, let me not make my life too miserable. Let me just make it, oh, this will be pretty miserable, but I'll deal with it. Let's make that pi for t greater than pi. I may regret this. No. Let's not do this. No. I'm calling it. No. Let's make it 0. 0, yes, 0. I like 0. For 0 less than t less than 3, and let's make it 4 for t greater than 4. Let's start with this instead. Let me not start with the most complicated example. How about that? Stop being an idiot. You guys give me some initial conditions, whatever you like. Or float your boat, what you want. What do you want from me? Y of 0 equals what? You fill in the blank. 0. Y prime of 0. See, yeah, I'm gonna make that 3 though, because actually let me make it some other number I don't have on the board yet. 7. Okay, so first of all, first order of business, solve this problem is the problem. Okay. So first of all, I would say y prime prime plus y is equal to, what is it equal to? It's equal to u of t minus 4, right? First of all, I convert the discontinuous function into a formulation in terms of the heaviside functions, the unit step functions. Next, Laplace transform. So I've got s squared big Y, right? Minus s times y of 0 minus y prime of 0, if I recall correctly. You guys have got the sheet, so you can check me on that, right? But honestly, this is the kind of thing you need to know without fumbling through the sheet to find, right? Otherwise, you're wasting your time. You need to work enough problems so that this is kind of ingrained, right? This should start to be ingrained after a little bit. Am I right, though? Table 7.2, look at the second thing, right? S times f of 0 minus f prime of 0. So yeah, I think we're right. And over here, this is the Laplace transform of the unit step function we just worked out and I erased, right? So what we got? We've got s, oh, come on. Look at that. Is this a minus? Yeah, don't wonder. Just interrupt me and say, is that supposed to be a plus? Because you're probably right. We've established this last class, right? So you guys got to have more confidence in yourself. Let's see here. S squared plus 1. I'm sorry, what is this? You know, it's one of the good things about this room is we can actually literally not put our chairs into a circle and talk about our feelings in here. So I feel like it's part of what sells this room. But, so what am I? I shouldn't tell the story anymore. Okay, let's see here. Plus 7 plus 1 over s like that, yeah. So just like, yeah.
I was going to say, could I get like a 30-second review of how you went from your y double prime plus y down to that next line?
I took the Laplace transform of it. So Laplace transform linear, I Laplace transform the second derivative. That wraps the initial conditions into these terms right here, right? And then the Laplace transform of little y is just the big Y. So there it is. And then the Laplace transform of the unit step function, of course, is this guy. So then we do algebra. We solve for big Y. That gives us big Y equals to 7 over s squared plus 1 plus 1 over s times s squared plus 1 e to the minus 4s. Now, in order to calculate the solution, I need to take the inverse Laplace transform of this, right? So y of t will equal to the inverse Laplace transform of 7 over s squared plus 1 at time t, plus the inverse Laplace transform of f of s times e to the minus 4s. I shouldn't use f. Let me use big G. Well, actually, it's okay. I'm going to use f here. And I'm going to go back and call this thing something else. Would you guys? I'm putting f tilde on it there. There. It's no longer f. Okay? I don't want that to be identified with this f. But at the same time, I want to use the theorem over there, which I've written for a big F. So that's my notational quagmire. I'm finding myself. It's really like no more than about an inch of quicksand. It's not much. Don't worry. Okay, so we already know how to do this, right? This is, we got that last class, right? This guy, 7 what? You guys tell me? How do we get 7 over s squared plus 1 from a Laplace transform? That comes from what?
Is it a cosine?
Indeed. We have a, oh, no. Sine, yeah, 7 sine.
Oh, so close.
Yes, so close. 7 sine of t. And then plus something over here. Now, to do that, we actually have to, the theorem, right? We're going to use the inverse Laplace transform of e to the minus 4s times f of s, right, is equal to f of t minus 4 times u of t minus 4, where f of t is equal to the inverse Laplace transform of big F of s. But you see, in order to make that formula work, we actually have to be able to calculate the inverse Laplace transform of the big F. What is big F? It's this, right? We can't calculate the inverse Laplace transform of that just yet. We have to do partial fractions to convert it into a form that we can actually calculate the inverse Laplace transform of the big F. So, usual song and dance, a over s plus bs plus c over s squared plus 1. Multiply by the denominator both sides, you get 1 a times s squared plus 1 plus s times bs plus c. By the way, these partial fractions, you need to get faster at them than you are wherever you are. I'm sure you need to get faster. But you should always remember you can check your answer as well, right? Like, don't suffer in confusion too long. Like, try it. Try to figure it out. But remember that you can always go to Wolfram Alpha and just type in the expression. And even if you don't say partial fractions, like in the list of things it produces, it'll probably produce the partial fractions if you just go looking for it. If you just Google partial fractions calculator, you'll find one. There's some really nice ones out there. But it is something you also need to learn how to do for yourself, right? So those are a good help to learning, but don't let them be the thing that produces your homework. Otherwise, there's a test. I don't have to tell you that. You know that by now. Let's see here. But again, I am teaching this next semester, so there's that. But let's not bring that into it. So let's see here. S equal to 0 gives us 1 is equal to a plus 0. Yeah, I like this equation. That's pretty good. Okay, so a is 1. A. And then the other ones are less pleasant. Let's see here. This is actually equal to as squared plus 1 plus bs squared plus cs. So one thing I could do would be differentiate this equation. It gives me 0 is equal to 2as plus 2bs plus c. And then if I plug in 0 into that, that's pretty nice, right? So s equals to 0 implies c is equal to 0, which is pretty nice. Once I know that, I can put s equal to 1 into that equation, and it gives me, 2a plus 2b equal to 0. In other words, a is equal to minus b. Well, let's be more useful. B is equal to minus a. I already know a is 1, so b is minus 1. So there's a trick that you can use. Differentiate your equation if you don't like the one you got. I mean, this holds for all s, so I can differentiate it if I want. Or you could just plug s equal to 1 into the original equation. I mean, whatever. It's up to you guys. Anyway, one way or another, you have to find your way to this. We've got 1 over s, right? And what did we figure out? B was minus 1, right? So minus s over s squared plus 1. And there you go, right? So what does that make my inverse Laplace transform of this? Gives me f of t, right? What's f of t equal to? 1, right? Yeah, now we got the cosine. Minus cosine t. All right. Now what I have to do, now here's where the thinking, look at this. We got f of t is this, right? We're using this identity right here, right? And that's going to allow us to calculate this right here. So I go, okay, I need f of t minus 4. So plus parentheses, 1 minus the cosine of t minus 4. That's my quote-unquote f of t minus 4. And then, unit step function, t minus 4. And there you go. That's the answer. Any questions? I mean, we can graph what's, yeah.
So we don't need a unit step function on the first function?
No. I mean, you could write u of t there if you wanted. But no. So the original term is the response to the initial conditions, right? That 7 produces this 7 sine t. So if I was to graph this thing, it's like 7 sine t, right? Up until time 4. At time 4, this thing turns on. Boom. And what's that do at time 4? That becomes, well, that's 0 originally at time 4, right? At t equals to 4, this is 1 minus 1, which is 0, right? So initially, this doesn't do anything. But then as time goes on, we add this term in, right? So I don't have a good sense of graphically what this thing looks like. I mean, you could work that out. So you've got 7 sine t, right? For 0 less than t less than 4. And then you've got 7 sine t minus the cosine of t minus 4, right, plus 1 for t greater than 4, right? So this, let me underline it in green, this thing, right, when you take sines and shifted cosines of the same angular velocity, like these both have omega equal to 1. They're the same frequency, sine and cosine. They're the same kind of sinusoids. What's going to happen is those can be combined into a single sine with a phase angle and the appropriate amplitude using the method of phasors or whatever floats your boat. So that term is just going to be like an amplitude times a sine with a shifted phase angle. And then the 1 shifts the whole thing up, right? So like after, I'm not sure exactly how big that is. It's probably about the same. So it's something like, here's 1, roughly speaking. So after this, it does some sort of thing where it's I can't do it. I failed. I'm trying to. So the new 0 for the new solution is about 1, whereas before it was about, it was about, the oscillation was about 0 to start with. After that force, that constant force turns on, the oscillation is about position 1, as it turns out. So it's like, that's a constant force pulling on a spring, so if you think about what that does, it's just always keeping the spring a little bit further out, but there's still oscillation in the spring back and forth, but now around a new normal, like a new equilibrium, so to speak. This is kind of the same thing that happens when you have a spring under gravity. If you take a spring under gravity and you let it oscillates in the same way as if that same spring had been put horizontally and let oscillate along a frictionless plane. It's just the equilibrium shifts down, and the oscillation's around a new equilibrium, comparatively speaking, everything else just being turned over sideways. That's actually, you could say that this is a derivation of that, if you're sufficiently adventurous. But anyway, think about how we would had to solve this before Laplace transforms. Yeah, okay. This is still a pretty easy example though, isn't it? Tell you what, let me do some projecting. I think I should do, let me, one more thing before I project though. So the full problem is always kind of a pain because, you always end up needing to do an inverse Laplace transform somewhere. And anytime you have an inverse Laplace transform, there's a pretty good chance you're going to need to do partial fractions. And it just, just requires algebra, right? But it's algebra that also has to filter through those theorems, which makes it more challenging, right? Let's just look at an example. Let's suppose f of t is equal to, I don't know, t 0 less than t less than pi, and then sine t, pi less than t less than 2 pi, and then 1 for t greater than 2 pi. Okay. We can work through this. We should be pretty good on our skill set here in terms of taking Laplace transforms of these sorts of things, at least. There's some issues in this calculation we're going to come to that you haven't thought about yet, I don't think. Okay, so what we got here? We've got t times u of t minus u of t minus pi, right? Plus the sine of t times what? Times u of t minus pi minus u of t minus 2 pi. And then plus 1 times u of t minus 2 pi. So I can rearrange this stuff because I'm interested in, I'm leading up here, guys, to taking the Laplace transform, all right? That's where we're going. So this is sine of t, u of t minus pi. Oh, I'm sorry. I was going to put that outside here. Sine of t minus t, right? U of t minus pi. And let's see here, plus what? 1 minus the sine of t, u of t minus 2 pi. The reason I do that is so that when we take the Laplace transform, we don't have to apply the formula with the green g too many times. Like, we're going to apply this formula 3 times. If I just multiplied it out and didn't think, I might apply this formula 5 times. 3 is better than 5. All right, so let's take the Laplace transform then. The Laplace transform of f of t, right? Laplace transform of t is what? It's the, is it 1 over s squared, or is it minus 1 over s squared? I can't remember. I think it's 1 over s squared. I think you're right. Yeah, 1 over s squared. Then, okay, so that's that term. Great. Not much to think about there. Now here, what's the Laplace transform? So we're following this rule here, which says that, actually I need to follow the rule, right? So I was using my cheat on the first term, but the next one, I'm supposed to do e to the minus a pi, right? Right? Oh, I'm sorry. Still wrong. E to the minus what? Pi s. I'm an idiot. We've established that already. Let's see here. E to the minus pi s times the Laplace transform of what? Yeah. Not t, not sine of t, right? This, exactly. So this is playing the role of g of t over there, right? So what I have to put down here is g of t plus pi. That's what the formula tells us. So I have to put t plus pi here. Of course, minus t minus pi, that's easy enough. I mean, and then this, e to the minus 2 pi s times the Laplace transform of, well, 1 evaluated at t plus 2 pi is still 1. And then minus the sine of t plus 2 pi.
Is that t times negative pi or minus pi?
Minus pi. I'm evaluating t at t plus pi, which gives me, if you want, I could do it this way. If that would be more conceptually translucent. Oh man, this choice of pi makes this too easy, but yeah, it's easy as pi. Let's see here. But is pi really that easy? I don't know. Like, why is pi easy? I'm not sure why that's a saying. Not sure it really makes sense. Let's see here. Sine of t, cosine pi. Plus cosine t, sine pi. I mean, pi is kind of a mess. So here, minus t, minus pi. I'm writing this out because, you know, if instead of having pi, I had like pi over 2, this would be a little bit more, I don't know, generally speaking, all these things don't go to 0. A lot of things I'm writing here are 0, though. Okay, I can't do it. This is sine of t again, isn't it? I mean, using the 2 pi periodicity of sine, right? Sine of t plus 2 pi is sine of t. But the sine of t plus pi, because of the adding angles formula, or however you like to see it, this is 0, right? This is minus 1. So 1 over s squared plus e to the minus pi s, parentheses, the sine t, Laplace transforms to 1 over s squared plus 1. But don't forget my minus, right? The t transforms to 1 over s squared, but there's a minus, so minus 1 over s squared. That pi transforms to minus pi over s, all right? And then this guy, minus 2 pi s, parentheses, 1 over s, minus 1 over s squared plus 1. So as a bit of intuition, in the time domain, the discontinuities are addressed by the presence of unit step functions, right? But in the frequency domain, the presence of discontinuities in the time domain, how does it appear? What's the signature of it? Exponentials in the frequency domain. These are what appear when we have discontinuities in the time domain. And when you have these, you have to treat these with care. These have to be viewed through the lens, through the appropriate formulas. They have to be viewed through these things right here. This is how we bridge the gap between the time and the frequency domain when we either have unit step functions in the time or the exponentials in the frequency in the transform domain. Like, you have to go through these. Don't just ignore the exponential and treat it like a constant or something. It's not legitimate. You have to go through these. Yep. But anyway, if you can understand this example, you probably can do pretty much any of them. Let me look at some let me use the projector, see if I probably lack imagination in my current comments. That's the Laplace transform. Yeah.
Oh, that's all you wanted to.
Yeah, I just wanted to. Yeah, if you tack this onto, let this be the forcing function to some differential equation, it becomes ever so much worse, because then we'd have to solve for the big Y, which inevitably would do what? It would force us to do things like divide these things by something else. After dividing those by the characteristic equation in S for the differential equation, we would then have to do partial fractions on the functions which were appearing as coefficients to the exponentials in S. After all of that is done, then we can feed it through the red boxed formula to go back to the time domain. Yeah.
That's something we're going to have to do.
Possibly. But probably more like an example that we had at the start of class, and not this one. Like, will I ask you to calculate a Laplace transform like this?
Yeah.
Oh, sure. Will I tack this problem onto a differential equation and find the solution to said differential equation? Not if I know what's good for me. I have to grade your work, and I have to write a solution too. I don't want to solve that either. I mean, not unless I'm getting paid considerably more money. I mean, if someone kidnapped my children and said, solve this differential equation, otherwise something happens to them, I mean, I'd do it then. There's any number of things that would make me do it, but, you know. Yeah. All right. Come on. All right. I would like some media, please. Please? Please? Yes. Ooh. Here, let's see if it can do two things at once. I think I can crash it. Ooh. Fancy pants. Did I ever tell you guys about the time I watched Army of Darkness at community college? So one day we were in physics, and my instructor brings up the Army of Darkness movie somehow. I don't even know how it came up, but me and Holly, who was in my class, we were like, what's that? And he was like, you've never seen Army of Darkness? We're like, no. He's like, watching it tomorrow. So like the next day, we took all of the physics time and like the time of some other class period just to watch this movie. Yeah, try that in here. Just don't start early. We can't do that. Here's something I didn't prove for you, but I should talk to you about the proof briefly. How do you prove that the Laplace transform of t to the n times f of t of s is equal to minus 1 to the n, the time derivative of that? It's actually really, really fun to derive. What you do is you differentiate the Laplace transform. Here's the n equals 1 case. So suppose you calculate the derivative of the Laplace transform. So that'd be like dds of that, right? So assuming that the derivative of s and the integration in t can be flipped, which is some analysis, okay? There's actually something to prove there. But not in this course. So yay, we move it inside. And then, so if you differentiate this with respect to the frequency variable s, right? Well, t is just there and a constant with respect to s, you know, so that just pulls down a minus t from the chain rule. Then you pull it out, and, well, you don't pull it out, I mean, you pull the minus out, and then that's t times f, that's the Laplace transform of tf. So there's the theorem in the n equals 1 case. And so this theorem just comes from successive differentiation of the Laplace transform. It's actually really, really easy to derive. Actually, I said it was some argument similar to the ones I did last time. That's just nonsense. I mean, is it similar to what we did last time? Sort of. I mean, it involves the Laplace transform's definition. in calculus, but other than that, I think that's a little bit of a stretch.